Hi everyone, good evening, or rather by this time, good night. My name is Artash. Thank you for letting me speak here today. Today, I'm going to be talking about using hybrid machine learning models to remove noise from exoplanetary observations using simulated data from the ARIEL Space Telescope. So, first off, you may have noticed I said simulated data, not real data. This is because the ARIEL Space Mission will be launched in 2028. It's a medium-class mission by the European Space Agency in collaboration with NASA. In its 4-year mission, it'll observe over 1,000 exoplanets. Now, enough about the ARIEL telescope. You might have remembered 2 years ago at the Carr Astronomical Observatory Open House, Dr. Sarah Seeger came and gave a presentation about the TESS Space Telescope. She talked about how the TESS was going to observe exoplanets around bright stars in the proximity of Earth. This is actually very similar to what the ARIEL Space Telescope will be doing. So to detect exoplanets around stars, the TESS telescope stares at the star, and when the planet passes in front of the star, the brightness of the star will dip and form a light curve. And that is how we detect an exoplanet. But how is the ARIEL telescope different? We have many missions similar to TESS to observe exoplanets. There's the retired Kepler telescope, the TESS telescope, the retired Kepler telescope, but this is going to be different because these telescopes have more been wide-scale observations. So for example, the TESS was going to observe the whole 360 degrees of view, so have a very large-scale survey. But the ARIEL telescope will specifically measure different stars that have already been planned out and do further analytics on those stars. So another difference about this telescope is that previous telescope used to measure in one wavelength or a couple different wavelengths. But the ARIEL Space Telescope will measure the dip in light for those stars in 55 different wavelengths. How is this helpful? Well, let's say we're observing the exoplanet in 2 different wavelengths. In the first wavelength, the atmosphere of the exoplanet is absorbing all of this wavelength. So this is an additional blockage of light coming from the star. So the dip in light that we observe will be deeper or have more depth than the rate that it actually is. Now, if we look at a second wavelength, in which case the atmosphere of the planet is actually letting the wavelength pass through. So in this case, there won't be as much light that's being blocked off from the star. So the depth of the light curve will be slightly less. So in these 2 cases, if we try to measure the radius of the exoplanet, we'll have 2 different sizes. How can this be useful? Well, with 55 different wavelengths, we're able to find which wavelengths are being absorbed by the exoplanet atmosphere and which wavelengths are being passed through the exoplanet atmosphere. This can help us find the actual elements in the exoplanet atmosphere. But there's one problem with this. When observing the star, there are also several stellar spots on the surface of the star. And this can cause interference when you observe the light curves in all the 55 different wavelengths. For example, here in this graph, you see a light dip, but there's several small bumps that are also there that are basically created by stellar spots. And this can stop us from accurately observing the dip in all the 55 different wavelengths. So we have to solve this problem. That's why I decided to turn to machine learning. Machine learning is very good at analyzing patterns in large amounts of data. And here, in the ARIEL Space Mission, they have provided a simulated dataset of over 120,000 different exoplanet observations in all the 55 different wavelengths. So first we have the time series data, so data that follows an order, here as a three-dimensional array for 146,000 observations. But we also have numerical data, so data that doesn't have an order. This is data such as the temperature of the star or the brightness of the star that we are observing. And this can help us find more about the star and help us accurately remove the noise caused by the stutter spots. And as an outcome, we need to predict the star to planet radius ratio for each of these different wavelengths. And basically this is the same thing as the depth of the dip in light created by the exoplanet going across the star. But I realized since we have two data sets, I can't use just one machine learning algorithm for both the data types. So for the time series data, I would have to use a model that can analyze time series data. So I decided to use LSTM neural networks. This is a type of recurrent neural network and can analyze patterns in time series data. So it learns in the light curve which are the areas that are more important to learn and which ones are less important to learn. For example, in the dip of light, it'll learn that the important parts might be the beginning, the end, and the middle. Now, for the numerical data, the data that doesn't follow in order, we need to use a different kind of machine learning algorithm. So I decided to use a feed-forward neural network, which is a neural network that is capable of analyzing patterns in non-time series data. And this is a slightly simpler neural network. So I made two different models. The first model would only look at the dips in light in the 55 different wavelengths for the planet. So this is kind of like a baseline model that I created when I used the whole data set. So this would pass the three-dimensional array through 3 LSTM layers. So again, encoding different and more complex levels of patterns inside the data. This will then be connected to a dense layer, which will output the 55 different planets are radius ratios for all the 55 different wavelengths. Now, this only used a part of the data, and so was not actually accomplishing its full potential. So, the new neural network that I made used both the data types. So, the light curve data, as well as the star parameters, so the star temperature or brightness. So, the light curve data was passed through 2 LSTM layers, and the numerical data was passed through 2 dense layers. Then, these 2 submodels were merged into one model through a concatenate layer, and then passed through a dense layer to get the final output. So once again, the 55 different radius ratio values. So I trained both of these neural networks on the data set over the period of a couple of hours. And so here the red line is the hybrid model, so the model that used the full data, and the blue line is the one that only used the light curve data. So you can see that the hybrid model reaches a much lower loss. So in this case, it's better to have a lower loss, unlike in accuracy. And it's also much more stable. So the blue line is shaking a lot, so has a lot of disturbances inside it, so it's not constantly learning about the data, unlike the red line. So now I took this model and then actually applied it to values in the test data set. So in this case, the blue line represents the actual radius ratios for each of the 55 different wavelengths. So on the x-axis, you see the 55 different wavelengths, and on the y-axis, the amount of dip for each of the wavelengths. So the model, as you can see here, is able to get a pretty accurate result. So a value that is very close to the actual results. So in conclusion, my model is able to get a mean squared error on the data of 0.001 on the test data set, and it also works on 2 different data types, so the time series data as well as the numerical data. So it's a very customizable model, so if we have more data that we want to use from the observations, then we can easily add it into the model and retrain it. So now that my machine learning model can predict the dip in light accurately for each of the 55 different wavelengths, how can we actually get the composition of the atmosphere of the exoplanet? So on the left, you can see the 55 different wavelengths on this side, as well as the dip in light on the y-axis. Now, from this, we can actually get the elements, or the amount of elements of, for example, carbon dioxide, carbon monoxide, water, methane, for each planet. So here you can see CH4, we're getting a different value from, for example, P cloud, which is a much higher value. And this is basically the final result that we want to get. So once this telescope actually launches, then if we apply this machine learning model to the data that it collects, we can actually approximate what are the levels of different compounds in the atmosphere of exoplanets. So actually all this data sets were part of the ARIEL challenge, the ARIEL data challenge, and I was one of the winners of the challenge, so I was invited to present the research and the model that I created at the ARIEL Open Community and Science Conference in Netherlands. So here you can see the schedule of the conference. And this is not the end though, because there are many ways we can still contribute to the ARIEL mission, even though Canada is not actually a part of it. The ARIEL Space Telescope has launched an open source project, because when the ARIEL telescope actually gets launched in 2028, we want to already know exactly where are these stars, and when are the exoplanets going to transit these stars, because that's the point where we actually want to make our predictions. So this initiative, it has an app that you can download, and it's for any astronomers that want to join, and they will be given stars that they want you to observe, and you can note when the brightness starts decreasing, so when is the exoplanet passing in front of it, and send this data back to the ARIEL mission team. And anyone with a small observatory or small or medium-sized telescope can actually participate, and this would actually be a great project for the RASC robotic telescope. Now, this is a very interesting project, I think. So many people would probably want to keep going with it, or follow or make their own model to make these predictions. So I made a training module, so anyone can download this training model, and it'll walk you through the whole data set and how you can construct your own model to solve the challenge. So this will help expand the knowledge of people know on the ARIEL Space Telescope. And I would be happy to conduct a workshop for any classroom or anyone who's interested. I actually gave a similar workshop at the MIT Media Lab a couple months back, and it was a success. Everyone was able to participate and make their own models. So I think that this training model is actually very useful. You can find the link on my GitHub. So my code is Artash N. And thank you. I'll be happy to answer any questions. Please go ahead.
Hi, okay. Thanks, it was really interesting. And I did watch some of your stuff that was available.
Thank you.
Did you do some Python programming yourself and used MATLAB or something like that as well? Is that one of that? I don't know. I didn't look at that.
Yes, you're correct, actually. I did use Python to program my model. So I specifically used TensorFlow, which is an open source AI library for AI in Python. So it's very useful. Yes?
I guess my question could be phrased two ways. How generally useful is your hybrid machine model? Or I guess the flip side would be, how many data sets look like that ARIEL data set that then you could put your hybrid learning model to analyzing?
Yes. So, first off, the data set that's trained the model is simulated. So, it tries to emulate the conditions that we will see generally for exoplanets as the conditions applied, so brighter stars closer to us, because as the star is farther to us, it's even harder to distinguish the exoplanet that's passing in front of the star, because in the ratios, it'll be even farther from us. But otherwise, it's close to the real truth values that actually happen around us. And so, yes, it could be applied accurately to a more general range. And also, most telescopes don't have 55 wavelengths of light curves that they can observe for each star. So, but this model can also be retrained with either less wavelengths or perhaps more wavelengths if we add them. So it's very customizable, can be applied to most of the observations.
Any more questions?
Yeah, just about the, I guess the time series component of the model. So is that actually what you're using to predict the light curve over time with the LSTMs?
The light curves, yes. So if I go back to the original data. Yes, so we have the two data sets. So we have, as I said, both the light curve data set, so data set with the light curves for each of the 55 wavelengths during the observation, as well as the star parameters. So we're using both of these data sets in the hybrid model to compute our final value. So that's the model that achieved a higher accuracy than the one that just used the wavelength data. That answers your question?
Okay, so you're predicting every wavelength for every
wave.
point in time. Okay,
Yes.
cool.
But the model runs through all of them together because they're also related since they're part of the same exoplanet. Thank you.
Very good. Thank you again.